So far, we got a big picture of the problem, which is how to find a joint distribution, the distribution of one function of two random variables. So in the previous video, we defined dz. So let's say this is xy. This is xy values, okay? And this is the line, let's say z. So for a point z and z plus dz. So when dz is very small, so we defined an inverse of this area, which is dz. And we said that the joint CDF is equal to integral over this area. And also we defined this is for this inverse of this area is going to be another bigger set, and the difference is going to be the band here. And then we said the PDF is the integral over this area divided by this set. So now we want to make this big picture more details and step by step. So I know that many of you love your dad, some of you may not. But this DAD method is the abbreviation for draw a diagram. So in order to simplify this method, we want to present a systematic method that you could solve difficult problems. So in order to determine PDF or CDF of g of z, we follow some steps, step-by steps, like what we had in previous chapters. The first one is to sketch the function. This was the DAD method for one random variable. The first step was to plot the function, like you had this function. So you have a diagram. To determine the range of values that x varies, x can take on, and so on. So this will help us to quickly figure out the range of values that y will take on. For instance, if you have a sinusoidal, y will be between -1 and 1 and so forth. So this method can be generalized for multiple random variables and so on. But instead of one dimension of one axis x, you have two dimensions and so on. And then you can say that if y of y for one single random variable is 0, wherever the value when the y equal g of x has no solution, has no solution, you could quickly say that the PDF is 0. The same thing applies here. So you could at least solve half of the problem to say where PDF is 0, where is non-zero. Let us have some examples, and we will follow the same routes and determine this one. So we want to draw a diagram. So in this first example, we want to find the CDF or the PDF of the sum of two random variables. So what we have here is that I have z is equal to x plus y. So I want to draw a diagram of, let's say, for a fixed value of z, I want to plot this one. If z is equal to 0, I will have x plus y equal to 0. So my solution will be this one, this line. So this is x plus y equals 0. Now if I put z equal 1, I get a line like that. So in general, this point is z. If z is negative, you get a line that, okay? So this is the line of z equal to x plus y. Let me clean up here a bit. Okay. Now, if I want to say that I want to determine dz is the set of all points x and y on these two dimensions such that such that g of x and y is smaller than or equal z. Okay, so basically for this example is that x plus y shall be smaller than or equal z. So this line x plus y is exactly equal to z, so this line is included. Now the line below, the points below this line satisfy this inequality. So this area which is yellow area, any point below this line is in dz. Yeah. If I plot the line of, because I have to replace z by z plus z plus dz, if I equate it with g of x, so it becomes x plus y, it will become a line that. So this point is z plus dz, and this point also will become z plus dz. So this set is d of z plus dz. So I have to subtract this one from it. So delta dz is going to be the set of all points x and y such that z is smaller than x plus y and smaller than or equal to z plus dz, which is this blue shaded area. So in this area. So what I could say here that is that the CDF f z of z is equal to integral, double integral obviously, of f x y of x and y dx dy over this dz. And this dz is plotted here. And f z of z is equal to 1 over dz. And then again a double integral over this blue shaded area. So, and then the joint PDF fxy of x and y dx dy, and then this area is delta dz, which is you have to integrate over this blue area. So how to determine the boundaries of these integrals in order to expand these blue areas or the yellow area and so on, we'll have more detail here. So I summarize. So this appears to be a line, and you could plot these areas and discuss it, and then we could see that this blue area is delta dz and dz is the yellow one, and we want to determine the boundary of the integral. For instance, if I want to do integral over dz, so this is integral. Now suppose that you are dancing. We want to dance in the yellow area and we want to cover all the points. So what are the range of variation if you are an arbitrary point in this yellow area? What is the minimum value that x can take on? So x could, if you go toward this direction, so the range of variation for x and the range of variation for y. So the minimum value that x can take on is minus infinity. Now, for a given value of x, if your x is here, okay, if you go up on this line, we have this equation of z equal to x plus y. So on this line, the minimum value of y is minus infinity, okay? And the maximum value of y is this point, which is from solving from this equation, which is equal to z minus x. Okay, but this point could be here, or could be here, or you could go toward this direction. So x could be plus infinity. So if you integrate over this area of fxy of x and y, and then dx dy, if you do this double integral, you get fz of z. So in this example, I put the first argument of the integral. Oh, I made a mistake here. So this should be, because the first integral is in terms of y, and then you integrate with respect to x. So the outer integral is x and the inner integral is y. I could have done the other way around. So you could say another equation here, and you could say y varies from minus infinity to plus infinity, and then integral over x from minus infinity to z minus y, and then fx y of x and y, and then do first integration with respect to x, and then do integration with respect to y. Both solutions will lead to the same result. If you do integration over the blue area, the joint PDF of fz of z times dz is equal to double integral over this delta dz, which is equal to, you have to put the boundary of this integral of fx y of x and y, and then dx dy. Now let's see how we could determine these boundaries. If you're dancing in this blue area, let's say if I want to put x as the outer integral, x varies from what to what. If you go toward this direction, your x coordinate become minus infinity, but if you go toward this direction, your x becomes plus infinity. So the outer integral, the range of variation x, the ultimate range of variation for x is from minus infinity to plus infinity. But for a given value of x, let's say your x is here, okay? So if your x is here, your range of value will be from this point to this point, because you are bound to be between these two lines. So your range of value for y starts from the lower line to the upper line. So from the lower line, if I solve it from this equation, I get y is equal to z minus x, and from the upper one, y will become z minus x plus dz. So if you do the integral and then divide it by dz, you get your PDF. So you see that drawing this diagram helped me to write the expressions, the boundaries of the integral, and so on very correctly. So in this example, I summarized the discussion we had here. So fz of z, this time I put the outer integral on y. So you remember that if I put y here, the second argument is here. So because you have to do the first integral with respect to x, and then these represent the equation of the lower line. These represent the equation of the upper line. Okay. Now this function you could simplify it, because you could change this dummy variable. You could change this one, which is x. You could change it to some simple changes. You could subtract y from both of them, or z. So you define. So if this dz is very small, let's say on this line. So you are in this line. I'm sorry. Let's say you are on this line. If this dz is very, very small, you could say that this function remains constant. So because it is constant, this function takes its value at this point or this one. So this function at point x takes the same value that it takes at this point and this point. So you could say that I substitute this x by this one. So you substitute z minus 1 here, and because this becomes constant with respect to x, it can come out of integral. So if you integrate a function from a to b, and of, let's say, c is constant, d of, let's say, x, this will become c times the difference, c times b minus a. So if you assume that this function z is very small such that this function is constant in this interval, so you could say that this integral, the inner integral, is equal to this function at this value times the difference. And the difference of the upper one and lower one is dz. And then dz is constant, comes outside of the integral, and you get this one. So now you can simplify both sides of this integral, and you get this one. So this equation is giving you the PDF of sum of any two random variables.